Today we are going to discuss about the topic fundamentals of the analysis of algorithm efficiency or the analysis framework. So generally we have two computing factors, that is space complexity and time complexity. We shall see in detail in the coming part. And the third one is measuring an input size, fourth measuring running time, and the fifth order of growth. So let us discuss about measuring an input size. So if the input size is longer, then the usually algorithm it will run for a longer time. So we can compute that the efficiency of an algorithm as a function to which the input size can be passed as a parameter. Let's take an example. Multiply 2 cross 2 matrix, know the order of these matrices. Then to multiply this, actually we must know the enter the elements of the matrices. So its time complexity is measured in terms of FC, and we first identify the logic operation, that is a step 1 of an algorithm, then the basic operation, and we have to determine the more time consuming, such as like how much it is located in the inner loop and how much time it consumes. And the second thing is that COP, it means that execution time of an algorithm's basic operation on a particular computer, and C of n is the number of times this operation needs to be executed for this algorithm. Then third one is T of n is that running time of the algorithm. So therefore it's expressed in the way of the formula T of n is approximately equal to COP of C of n. Let's see an example, which is sorting. So let's compare the elements and then place them in the correct positions. So this becomes a basic operation. So the first example is that searching element from list of n elements, and input size becomes the list of the n elements, and basic operation becomes the comparison, that is we are given a key to compare and search. So that becomes the where we perform searching becomes the basic operation. And the second example, we can see that our problem is matrix multiplication. Two matrices are given, that is our input size, and next the multiplication which we perform with the given elements is known as the basic operation. Same goes for the GCD problem. Next, we move on to order of growth. Order of growth says that we need to measure the performance of an algorithm in relation with the input size n, and this is called order of the growth. So let's take an example. The order of growth for varying input size of n is as given below. A table is given where for varying of input size, the order of the growth is given. Let's have a look at the table. The n log n, n square and 2 power n values are given, and we know how we can evaluate it. Now let's discuss about the worst case, best case, and average case efficiencies. So the worst case time complexity tells us that when there are no matching elements, or the first matching element happens to be the last one on the list, then it becomes a worst case complexity. That is, we cannot find the desired element in a short period of time or in the first one. So this becomes complex for the users or for the rest of the people to find their determined element or what they are in search of. So C worst of n is given to be n. So this algorithm runs the longest among all the possible inputs of that size. So the time complexity for linear search in worst case is big O of n. Then next one, we'll move into best case complexity. This runs fastest, and for example, if we see sequential search, if a determined element is to be found in the first one itself, then it becomes the best case. So C best of n is given to be 1. Its time complexity is big O of 1. Then the third thing is average case time complexity. So this complexity gives us with a specific random input. So the probability of getting a successful search may be in an average manner. So we are taking a total number of elements in a list, and we are performing a basic operation. It may be successful or may not be successful, but if we get it in a before the worst case, then we can say that it is an average case possibility, so that it becomes average case time complexity. So C average of n is equals to n plus 1 by 2. So there may be any number of elements, but at which chances of not getting element are possible, hence n into 1 minus p arrives. So the time complexity in this case is big O of n. Now let's discuss about asymptotic notations and its properties. As we have seen it in the earlier semester, the same follows, but we have to learn it according to this unit 1. So the big O notation, big theta notation and the omega notation are followed here. Here also we know that upper bounds and lower bound limits are followed. So it is a method representing the upper bound, that is big O notation, of algorithm's running time. So we can give the longest amount of time taken by the algorithm to compute using this big O notation. So we can say the definition as a function t of n is said to be in big O, that is of g of n, denoted t of n, which belongs to this O of g of n if it satisfies the condition that t of n is bounded above by some constant multiple of g of n for all large n. That is, if there exists some positive constant c and some non-negative integer n naught such that t of n is less than or equal to cg of n for all n which is greater than or equal to n naught. So a practical diagram is given where the upper bound curve is drawn. The second asymptotic notation is omega. So this notation is used to express the lower bound of the algorithm's running time. So using omega notation we can denote the shortest time, whereas in the big O notation we can denote the longest amount of time taken. So same this expresses but with a different same logic but with a different explanation. That is, t of n is said to be in g of n, denoted that t of n belongs to g of n if t of n is bounded below by some positive constant multiple of g of n for all large n. So here a practical curve is given which expresses t of n. There we saw it to be lesser than g of n. Here it is greater than or equal to cg of n for all n which is greater than or equal to n naught. And here a practical diagram is given where the lower bound is expressed. Now let's see about the asymptotic notation, which is the third notation, that is theta. So it is also expressed in such a way that both the upper bound and lower bound is expressed. So if there exists some positive constants, let's consider c1 and c2, and for some non-negative integer n naught such that it satisfies the condition c2 g of n is less than or equal to t of n, which is less than or equal to c1 g of n for all the n which is greater than or equal to n naught. Here in the practical diagram we can see the expression of the curves, which is both the upper bound and lower bound below and above the t of n. Now let's move on to the mathematical analysis for non-recursive algorithms. Here we follow some steps in order to obtain this algorithm. First one is we need to decide the input size based on the given parameter. Second, we need to identify algorithm's basic operation which has to be performed. Now the third thing is we have to check how many times the basic operation is executed. Now this is for non-recursive, so we have to set up the recurrence relation with some initial condition and expressing the basic operation. Now the fifth step is to solve the recurrence or at least determine the order of the growth. Let's have a look at the general plan for analysis. Deciding on the parameter, identifying the basic operation, determine the worst, best and average cases for the given or the taken input of size n. Then we are setting up a sum for the given number of times of operations is to be executed. Simplify the sum using standard formulas and rules. Now let's discuss about the mathematical analysis of non-recursive algorithm. We just count the number of operations over here. That is, loops will become series sums, so some series formulas are required to calculate this. So the general plan for analyzing the time efficiency of non-recursive algorithms are as follows. First step is to determine the parameter indicating the input size. Second, we need to identify the basic operation of the algorithm. Third, check whether the number of times the basic operation to be executed depends only on the input size. If not, worst, best and average cases efficiencies have to be investigated separately. Fourth step is to set up a sum which expresses the number of times the algorithm's basic operation is executed. Fifth one, we need to determine the order of the growth. Here, a practical example is given where these steps are applied to find the value of the largest element in a list of n numbers. For simplicity, we assume that the list is implemented as an array. It is given that we are taking it to be an array. Then, following is the pseudocode of a standard algorithm for solving the problem. First of all, we need to give out the algorithm for solving any kind of problem. Next, we need to determine all these 5 steps and find out the answers. This follows the non-recursive algorithm. Now let's see about mathematical analysis of recursive algorithm. Likewise, we saw in the non-recursive algorithms, it follows till the third step, and the fourth step differs. That is, we need to set up a recurrence relation with an appropriate initial condition for the number of times the basic operation is executed. So, fifth step is we need to solve them and find the order of the growth of its solution. Same goes for this. We need to find the algorithm describing about the problem, and next give out the 3 steps to be returned for the particular problem. Here we are taking the factorial problem and the formula is mentioned there. Next, the number of multiplications, that is m of n, needs to complete. It must satisfy the equality with which the condition is given. Hence, if it satisfies, we can find out the rest and apply to all of the recursive algorithms. This is all about non-recursive and recursive algorithms, which comes under mathematical analysis. Thank you.